Hi everyone and welcome back. Before starting to evaluate our model, let's import some additional libraries. We import NiBabel to load a full cardiac MRI scan, TQDM to get a progress bar when validating the model, and last but not least Camera from Celluloid for easy volume visualization. At first, we create a new instance of our model and load a checkpoint. Let's define a variable called model, to which we assign the model returned when calling atrium segmentation dot load underscore from underscore checkpoint, to which we pass the wait path. As mentioned in the last lecture, we directly provide multiple checkpoints. Let's use the most recent one for evaluation. You can find the checkpoints in a directory called waits. The most recent one is called 70.ckpt. Now we use torch.device, in which we check via torch.qda.is_available if a GPU is available, and if so, use it. Otherwise, we are going to use the CPU. Next, we set the model to evaluation mode and send it to our previously defined device. We are now ready to evaluate the model on the complete validation dataset. To do so, we define two empty lists called preds and labels. After that, we loop over our validation dataset to get a slice and corresponding label. Let's use TQDM to get the progress bar. Within the loop, we override our current slice by at first converting it to a torch.tensor, next copying it to the device, and last but not least adding the batch channel dimension. We then proceed by using with torch.no_grad to prevent PyTorch from accumulating the gradients to finally compute the prediction. After that, we append this prediction to our preds list. In fact, we copy it to the CPU if necessary and convert the tensor to a NumPy array. Subsequently, we append the label to the labels list. Last but not least, we convert both preds and labels to a NumPy array. That's the full evaluation loop. Let's run it to find out how our model performs. We can now compute the overall dice score for those predictions and labels by subtracting the dice loss from 1. We can access the dice loss by calling the loss function of our model. Let's write 1 minus model.loss_fn, to which we at first pass our predictions and next the labels. Note that as this is a PyTorch module, we need to convert both NumPy arrays to a tensor. Let's write torch.from_NumPy preds and torch.from_NumPy labels. Let's have a look at our dice score. Whoa, awesome! We have a dice score of roughly 0.92. This basically means that we have a perfect prediction. Only some really small errors might occur. To finalize this project, we will load a test subject from the dataset and estimate the position of the left atrium. To do so, we at first define the path to the subject. You can find all test subjects in the directory task02hard/images_ts. Let's load patient number 2. After that, we define a variable called subject MRI, which stores the full volume returned when calling nibabel.load_subject.get_fdata. As this scan is neither normalized nor standardized, we need to perform those tasks. Let's quickly copy the normalization and standardization functions from our pre-processing notebook. We now pre-process this scan by at first cropping 32 pixels from top, bottom, back and front, followed by normalization and standardization. Let's define one more variable called standardized scan, which stores the result produced when applying set normalization followed by min-max scaling to our cropped subject. We can now loop over the sagittal axis of this standardized scan to compute the prediction for each slice. Let's define an empty list called preds, which will store the prediction, and loop over the last axis. We use the current loop counter variable I to extract the corresponding slice of the standardized scan. After that, we at first prevent PyTorch from storing the gradients to finally compute the prediction. Note that our slice is currently a two-dimensional NumPy array. Therefore, we have to at first convert it to a torch.tensor object. Next, we need to add at first the channel dimension followed by the batch channel dimension. After that, we need to convert it to float because nifties are typically stored as doubles and not floats. And last but not least, copy it to the previously defined device. Whoa, what a statement. After that, we immediately remove the batch channel dimension and the channel dimension again. We now threshold this prediction with 0.5 and finally append it to the preds list. As usual, we copy it to the CPU if necessary. We are now ready to visualize the volume with the corresponding predicted segmentation. At first, we create our figure object by using plt.figure. Based on this figure, we create our celluloid camera object before finally looping over the last axis of the standardized scan. Next, we visualize the current slice of the scan. After that, we create our segmentation mask by masking all elements in the current prediction that are 0. Last but not least, we visualize this mask with an alpha of 0.5 before taking the snapshot via camera.snap. Alright, let's create the animation by using camera.animate. When we now import HTML from ipython.display, we can visualize this animation in our Jupyter notebook by converting it to an HTML5 video. We can now inspect the full volume in a slice-by-slice manner with the corresponding prediction for each slice. As you can see, the predicted segmentation is close to perfect. The left atrium is fully segmented in all slices except for a few edge pixels. Congratulations, you created a neural network which is capable of successfully segmenting the left atrium in cardiac MRI images. In the next project, you will build a segmentation model to segment lung cancer in CT images. Thanks!